So our objective today is that we're going to learn that not every atom of the same element is exactly the same. And by the end of this period, you should be able to tell me how you can identify an element by looking at a Bohr model. Okay? So, before we go on into these notes today, I want us to look back at notes that we already took. So I want everybody to go to page 43 in your notebook, which is the atomic structure and history notes. So it should have been on page 43, if I believe. Yes. So, looking at your notes from page 43, we talked about that day about the atomic structure, the subatomic particles, and so on. Okay? And we talked about the history of it. We started off by talking about the Greeks and how they came up with the word atom because atomos means not divisible, and they said that you couldn't divide it anymore. Then another guy came along, his name was Dalton, and he came up with a theory called Dalton's atomic theory. Okay? So that's what we're going to discuss before we go into today's notes. All right? So Brianna, could you tell me something that you have about Dalton's atomic theory? Okay. All elements equal atoms. Is that what you have written? Alright, so Brianna has all elements equal atoms. I think there's a little more to that. Can anybody add something to that? Yes, they do.
All elements are equal to atoms. Atoms are the same things. Atoms are different.
Okay, so the first one was that all elements are composed of atoms, right? The second one was what? Atoms of the same element are alike, which I think that's the one you're talking about. Okay? So atoms of the same element are alike. What was the next one? Atoms of different elements are different. And? Okay. Compounds are formed by a joining of two or more elements. Alright. That atomic theory still stands today except for we change one thing. Okay? His second part to his theory was that all the atoms of the same element were exactly the same. That means that every atom of oxygen looked exactly the same no matter where you found it. Every atom of aluminum looked exactly the same no matter where you found it. Well, now we know that's not true. So now we have changed that section or that part of the theory to atoms of the same element have the same number of protons. That's it. We don't say that they're exactly the same. And the reason we don't say they're exactly the same is because we have found something called isotopes. Isotopes are different forms of the same element. The same element, but different number of neutrons. So now we know that carbon atoms, they do all have 6 protons. Every carbon atom you come in contact with is going to have 6 protons. But they don't look exactly the same because there's 3 isotopes or forms of carbon. There's carbon 12, carbon 13, carbon 14. Which means that those 3 carbons, they're still carbons, but they're different in the sense that they have different number of neutrons. So, if you change the different number of neutrons, what within that atom changed? What part of the atom changed? The nucleus. Very good. Because, Tori, what's found in the nucleus?
The electrons. No. The neutrons and the protons.
The neutrons and the protons. So, if I change the number of neutrons, then I change the nucleus, right? So, how can I distinguish between a carbon 13 atom and carbon 14 atom if I can't see the neutrons and I can't count them? So what can I look at if I'm looking at atoms of 2 different ones? Not the atomic number, but the atomic mass. Because if I change the neutrons, doesn't that change how much they weigh? Yeah. So isotopes differentiate or are different in the fact that they all have the same atomic number because they all have the same number of protons, the same element. But they have different mass numbers or different atomic masses because since they have different neutrons, they weigh differently. Okay? So, whenever we look at that, we look at something called isotope notation. Isotope notation is a shortcut way of identifying isotopes. So in order for you to know what the isotope is and how to draw it, well, obviously you need to know the protons and electrons, and that's given to you by the atomic number. But you also need to know how many neutrons, and that you're going to get from the mass number. So when we're drawing isotopes, we're still going to use 8 to find protons and electrons, and man in order to find neutrons. But instead of the mass number on the periodic table, we're going to use the mass number that's given to us. So if I look at this isotope notation, what element is this? Hydrogen. And then I have a 1 at the top and a 1 at the bottom. The number at the top is always the mass number. So the mass number of this hydrogen is 1. And the atomic number of hydrogen is 1. Now this one is always going to be the same as the periodic table. So the atomic number will be the same as the periodic table. The mass number is the one that can be different. Doesn't necessarily have to be, but it can be. Alright? So from here, I should be able to calculate protons, neutrons, and electrons. Okay? So, Zach, how many protons does the hydrogen have? 1. Why 1? Very good. Because the atomic number equals the number of protons. Alright? Alright, Gabriel, how many electrons does that one have?
1.
1. Why 1? 8. What does 8 stand for? Atomic number. Very good. So it's also 1 because the atomic number is 1. Alright, now for neutrons, remember I used mass. Mass number minus atomic number equals neutrons. So Leslie, how many neutrons would that one have? None. Because? Very good. 1 minus 1 equals 0. So if I look at this, I'm able to look at the protons because of the atomic number. I'm able to get the electrons because of the atomic number. And then the neutrons is going to be mass number minus atomic number. Man, M-A, neutrons for N. Okay? Now, so when we look at isotopes, we're going to look at isotope notation, and then we're going to look at one other way that we can write it. Well, we calculate the same way. So let's look as examples. We're going to look at 3 isotopes of hydrogen. Now, isotopes sometimes are given different names. You do not have to memorize the names of the hydrogen isotopes, but I wrote them just to refer to them. Okay? You won't have to memorize any isotope names, but it was just something that I wrote in just because it makes sense to do so. So the 3 isotopes of hydrogen are called protium, deuterium, tritium. All 3 of those are hydrogen. So if all 3 of those hydrogen, Ethan, how many protons do they have? No, just each one. Each one, how many protons would it have if it's hydrogen? 1. Very good. So protium has 1 proton. Deuterium has 1 proton. Tritium has 1 proton. Because all 3 of them are hydrogen. They're called something different because they're isotopes and they have different number of neutrons. Okay? So let's look at the isotope notation of those 3. Now this you do have to write down just because of the examples. So protium's isotope notation is mass number 1, hydrogen, atomic number 1. For deuterium, mass number 2, hydrogen, atomic number 1. For tritium, mass number 3, hydrogen, atomic number 1. So by looking at those 3, Ricky, what do all 3 of those have in common?
They all have 1 proton.
They all have what?
They all have 1 proton.
They all have one proton because their atomic number is 1. Okay? So I know that all three of those are hydrogen because the bottom number is 1 and the atomic number of hydrogen is 1. Okay? Now, Princesa, what do they have different? The atomic mass, which in this case we call it a mass number. Because remember, atomic mass is with a decimal. So the mass number, 1, 2, 3. And let's see, Reina, what does that change? If my mass numbers are different, what does that tell me about the atom? That the neutrons are different. Okay? So let's draw. Alright, Jared, if I want to draw this proton, how many protons will I draw? 1. Okay. And how many electrons will I draw? 1. Okay. And how many neutrons will I draw? Remember, man. So how many? None. Why? How would I know there was no neutrons? What did you do to get 0? Very good. So 1 minus 1 here? Yep. Alright. And it's correct. So if I wanted to draw that, and yes, you should draw it, that's what I would draw. I draw 1 proton in the middle because the atomic number is 1. I draw 1 electron on the electron cloud because the atomic number is 1. And I don't draw any neutrons because 1 minus 1, which is mass number minus atomic number, gives me 0. Okay? So, Jocelyn, now let's do deuterium. How many protons will I draw for deuterium? Okay, 1. Okay, because the atomic number is 1. Alright, how many electrons? I'm sorry? Okay. Electrons? 1? Because? Okay. And then neutrons, remember is mass number minus atomic number equals neutrons, so how many neutrons? On deuterium, on the second one? What? Because? Okay, so what 2 numbers did you subtract? Okay, which in this case are what numbers? 2 minus 1. Okay? Alright, and that sounds correct. So in deuterium, I have 1 proton in the center. I have 1 neutron in the middle because of this 2 minus 1. I have 1 electron because of the atomic number. So then, let's do tritium. Okay, so, second. So how many protons would the tritium have? 1. Why 1? That's how many. Okay. How many electrons? 1. Because? Atomic number. Alright, and how many neutrons? 2. 1? Okay, because of man, so which numbers am I looking at? 3 and 1. Okay? And that sounds correct. Alright? So our tritium would be 1 proton, 2 neutrons, 1 electron. So looking at those 3 pictures, what is similar between all 3? They all have 1 proton and 1 electron. Now, remember I talked about electrons and protons always being the same, right? And that was when we're looking at the periodic table, it's a neutron. But remember I told you that eventually we're going to learn that they don't always have to be the same, right? When we get to bond. So electrons are not always the same as the atomic number if we're talking about bonding. Right now they are, but eventually they're not. Do protons ever change if we're talking about that element? No. So, very important, very important, very important, very important. What do you count when you're going to look for what element it is? Well, you cannot count. If I just gave you these pictures right here, what do you always look at to find out what element that is? The number of protons. Because in 2 weeks we're going to see that they don't always have the same electrons because we have charged atoms. Right now they do, but eventually they're not. Protons are what you look at in order to identify an element. Okay? So, how do you identify an element from its Bohr model? By looking at what? Okay, by looking at what?
Proton.
By looking at what?
Proton.
So we identify Bohr models by looking at what?
Proton.
That was too low. We look at identify Bohr model by looking at what?
Protons.
Protons. Okay? Not electrons, not neutrons, protons. We said that several times. It better be in your notes. It's important. Okay? So, let's practice a different way of drawing isotopes. So sometimes I'm going to give you the isotope notation and you can draw it like this. Pretty simple, right? Sometimes I'm going to give you the long way of writing isotopes, which is like this. Helium-3. I tell you the name of the element. Where would you find the symbol? If I tell you the name of the element, where do you find the symbol? Periodic table. And then sometimes I give you a number behind it. So helium-3 means helium with a mass number of 3. So the number that's behind the word is giving you a mass number. So helium-3 is telling you helium off of the periodic table, He. This 3 is a mass number, and where would you find the atomic number? On the periodic table. So, what if I just write helium? I didn't give you a mass number, so where could you find the mass number? On the periodic table. So, sometimes you'll get the name and the mass number behind it. If they give you the mass number, that's the mass number you use. If they don't give you the mass number, then you use the one off the periodic table. So right now, I want to give you about, you probably can finish in 3 to 5 minutes. I want you to go through and I want you to write the isotope notation for helium-3 and helium. And I want you to draw the atom for helium-3 and helium. So do that now. Yes, so this is in your notes. Compare with each other as you're doing it. So you're going to write the isotope notation for helium-3 and helium, and then you're going to draw helium-3 and helium. You're writing the isotope notation for helium-3 and helium, and then drawing. You're writing the isotope notation.
No, yeah. I'm thinking of hydrogen. Yeah, so it's 2, right? So 3 minus 2 is 1. So 3 that I put on our
But helium is 2.
it would be 2. exactly the same thing. We were able to go through one, I like to
Where is he?
it's like how did you understand? That's exactly what I was thinking. Oh my god. Was it the 2 and the 2? So what's that? 0 and 2. So what if we do so what's the mass number? So they don't need to the numbers and then the one offers the first numbers. So it was 2 minus 0.
Alright, who thinks they have it correct?
Jackie does.
Okay, Edwin. Okay, you didn't do your isotope notation. Who thinks they got the isotope notation and the picture?
That's like perfect, man.
Alright, so this is Jackie's. Let's look. I'm sure she did it correctly. Alright, so let's look at this. Alright, so looking at this first one. Remember isotope notation, you need to have your symbol, your mass number, and then your atomic number. So is this correct? Yes. He is the symbol, the mass number I gave you, which was 3, the atomic number is 2, which she got off the periodic table. So that's correct. Then you come over here. Your atomic number gives you your number of protons, which is 2. That's correct. And 2 electrons. Your neutrons is mass number minus atomic number. So 3 minus 2 gives you 1. So this is correct. Any questions on how she got that? Okay. Then I come over here, which I see is helium. Alright, so helium. Now, in this case, if I look at the periodic table, that's where I'm going to find the atomic mass, which is 4.00 something, right? So what is the mass number? And then that would give her 2 protons, 2 electrons, and 2 neutrons. Is that correct? Yeah. So, when I give you this, when I write helium 3, you're supposed to write the isotope notation and draw the picture. Any questions over that? Alright, so we're going to practice that again. But on the other side. So our notes are over. Now I need you to go to page 46, which is across from those notes. Okay, so we're looking at page 46. This is what we're going to do. Just like last time when we practiced drawing the atoms, this time you're going to practice drawing isotopes. Now, this is what I want. I want you to separate this page into 3 sections. These 2 are a little bigger, the bottom one's small. You're going to draw carbon 13. You're going to write the isotope notation and draw the picture. Carbon 14, write the isotope notation and draw a picture. And then the bottom, I want you to compare and contrast carbon 13 to carbon 14. What are the similarities? What are the differences? So, isotope notation drawn for carbon 13, isotope drawing for carbon 14. Similarities and differences in carbon 13, carbon 14. So, how are they the same? How are they different? Any questions on what you're doing? Now, I want you to discuss with your partner as you're doing it, especially if you're not really sure if you're doing it right. I want you to look back at your notes. When you are done, on your desk, you're going to have this lavender paper on there. It is practicing identifying atoms. So, what do we count to identify atoms again?
The proton.
What do we count to identify atoms again? What do we count to identify atoms again? Thank you. Alright, so make sure you do that correctly. Any questions? I'm sorry?
I teach
choose your partner.
that
You're just gonna have to.
one.
Yeah, because you're the gentleman, right? Alright, so that is what you need to be doing. Don't waste time.